Hey guys, here I am, Mr. Kilgore, talking about our expanded definition about acids and bases. And today we're going to talk about the Bronsted-Lowry definition of acids and bases, where we're going to expand uh, what we know as acids and bases. So we're going to identify acid and bases and conjugate acids and bases by the reaction. And we're also going to predict products of a reaction if we're given what substance is the acid or the base. So, quick recap. The Arrhenius definition of acids and bases is what we talked about previously, where Arrhenius acids dissociate forming the H plus ion. So, a couple examples of those are hydrochloric acid, which dissociates to H plus and Cl minus, and nitric acid, which dissociates to hydrogen ions and nitrate ions. Arrhenius bases, similarly, they are compounds which form hydroxide ions in solution. So NaOH dissociates to sodium ions and hydroxide ions, and calcium hydroxide dissociates into calcium ions and hydroxide ions. So those are the definitions which we talked about last class. Now we're going to expand the definition to include more things which behave as acids and bases based on proton transfer, proton being H plus. So acids are proton donors in a reaction, and bases are proton acceptors in a reaction. So let's see some context in this. So here's an example of an acid-base reaction. So we have NH3 plus H2O yields NH4 plus OH minus. So let's take a look at what's going on here. Let's look at the pairs. NH3 is the reactant, NH4 plus is the product. H2O is the reactant, OH minus is the product. So let's see what happened to both of these in order for this reaction to go from the reactants to the products. NH3 in the reactants became NH4 plus in the products. Now, how did that happen? Well, NH3 started with one N, 3 H's, ended up with one N, 4 H's, and a positive charge. H2O started with 2 H's and an oxygen, and it ended with one oxygen, one hydrogen, and a negative charge. Let's talk about why. NH3 accepted an H plus ion, hydrogen ion, becoming NH4 plus. Therefore, that's the base. H2O donated that H plus to NH3. Therefore, it is an acid. So let's go over in general how we can figure out a little more. The products also have names. They're called conjugate acid and the conjugate base. The conjugate acid is the product that has the transferred hydrogen ion. The conjugate base is the product that is left over after it transferred the H plus. So a lot of times people will say it's the acid and base in the reverse reaction, and that also is basically saying the same thing. So NH3 is our base. Therefore, our conjugate acid is going to be NH4 plus because that's what has the hydrogen ion in the end. The conjugate base is always the conjugate acid is always the pair of the base. The acid produces the conjugate base. The acid is what, once given that H plus away, will have the conjugate base remaining. So that's what's left over after it lost the H plus. Notice the conjugate acid will always have a 1 plus charge higher than the base. And the conjugate base will always have a 1 minus charge less than the acid. So let's, if you guys want, you guys can try this. I would pause it here, see if you guys can identify the acid, base, conjugate acid, and conjugate base. All right. It's a good time to pause and see if you guys can do this independently. Otherwise, I'm going to get going on that first one. So first thing we do is we find the pairs. So the pair to H2SO4 is HSO4 minus. So we want to compare them to figure out what changed here. So how does H2SO4 become HSO4 minus? Well, we look at what's different. There's two things. There's the number of H's and the charge. So what happened? H2SO4 donated an H plus. So therefore, it's an acid. Let's take a look at H2O. Compare H2O with H3O plus. How does H2O become H3O plus? Well, two things changed. Started off with two H's and ended up with three and a positive charge. So this H2O had to have gained an H plus. Therefore, it is a base. Okay. So why don't you guys think about it a little differently if you're having trouble. So let's think of H2O as HHSO4 and H3O plus is HH2O plus. So we're talking about transferring this hydrogen ion here. The red one is the one that's highlighted, that is transferred. So the H starts with the HSO4 in H2SO4. What does it have to be? Well, this has to be an acid because it gives away the H to the H2O. How do I know that? Because look what happens. Look where the H is in the end. It's with the H3O plus, or as I wrote it, HH2O. So therefore, this is our acid. The H ends up with H3O plus, as I wrote it as HH2O plus. Therefore, the H2O is the, the H3O plus is the conjugate acid. Label the rest. If H2SO4 is the acid, then H2O must be the base, and its pair must be the conjugate base. All right, so let's do another example here. Good time to pause if you guys want to try this independently. Otherwise, I'm going to go on and go over a couple more examples. So we look at our pairs here. The pair of acetate here is HCH3COO, aka acetic acid. Hopefully I didn't give anything away there. The pair of HNO3 is NO3 minus. So let's talk about what's different about the two. The H starts with the NO3 minus. It ends up with the CH3COO. So how does that happen? Well, the HNO3 donates its H plus. How do I know? Because in the end, it doesn't have it anymore. It got rid of it. It's left as NO3 minus, which is making HCH3COO the conjugate acid. So the acid is whatever has the H. If it's in the reactant, it's the acid. If it's in the product, it's the conjugate acid. So if the HNO3 is the acid, acetate must be the base. And therefore, NO3 minus is the conjugate base. So again, I'll go over another example. You guys should probably try to pause it here and see if you guys can do it independently. So figure out your pairs first. Figure out what happened to your pairs to end up like they did in the products. So, for instance, and it doesn't matter which one. You can start with NH4 plus becoming NH3. Now you got rid of an H plus. Or you can figure out that HPO4 negative 2 became H2PO4 minus 1. So either way, it's fine. And you'll always get the same results. But NH4 plus starts with the H, and the H ends up with H2PO4. Therefore, this is our acid, NH4 plus. If NH4 plus is our acid, then HPO4 2 minus must be our base, making NH3 the conjugate base, and H2PO4 minus the conjugate acid. So just a little quick thing about why we can include all of the Arrhenius acids and bases in the Bronsted-Lowry definition as well. You think about your dissociation equation where HClAQ, meaning aqueous, yields hydrogen ions plus chloride ions in aqueous solution. That's the Arrhenius way, the dissociation equation. Now, really, when you have an aqueous solution, you don't have a free hydrogen ion. You actually have it in terms of hydronium, and that's where we can use our expanded definition to include this. We have HCl aqueous plus H2O liquid because we are aqueous solution, so H2O is there, yielding H3O plus. So HCl donates the H to H2O, making H3O plus, and the conjugate base leaving at Cl minus. So really, according to the definition of Bronsted-Lowry, H3O plus is really how H plus aqueous exists, never just as a single proton. So another thing we can do is we can predict products here. So HNO3 plus F minus. Given that F minus is the base, let's talk about how we can predict products. So if F minus is the base, then HNO3 must be the acid. So that's an easy one because our reactants are both going to be acid and base here. So the F minus is a base, it must gain an H plus. So if it accepts that, what's going to be left over? HF. There's zero charge because the positive from the hydrogen ion cancels out the negative in the fluoride ion. The other product, if HNO3 is an acid, what's left over after it loses its H plus? Well, NO3 with a charge of -1. If you lose that positive charge, you end up with a negative, more negative charge. So that's our conjugate base right there. All right. That's it, guys. I hope this helps. I'll talk to you guys next time.